Hello everyone, welcome back to our YouTube channel Becoming a ROS Developer. I'm Desire and today we've got Jainam who has just completed the course Linux Basics for Robotics. So as usual, we'll first begin by seeing a demonstration of his code base running on the real robot, and then after that we'll get to the nitty-gritties of his project and get to ask him a couple of questions to really understand how he did his project, and if he encountered any problems, we also want to understand that. So without any further ado, I'll now hand over this platform to him so he can begin his presentation. Alright, Jainam, whenever you're ready.
Yeah, okay, thank you. So hi everyone, today I'll be demonstrating my Linux Basics project with the construct. And to start this off, I'll first be opening up the bring up program that is required for all real robot simulations. So then the left shell. And then next I'll be running up the ROS2 teleop in case something goes wrong with my robot.
Alright.
Next up will also be the robot interface. This program is actually required to run in other programs that I've discussed later on. So the optical loader, the robot statistics, these would require the robot interface to be running first. So that running also. Next up is and now finally is the program, the naive optical avoider.
Yes.
And I'll put that through. And as you can see, it's already started. And soon enough, you will see the real robot. And the robot moving in the real robot lab. As you can see, it's already detecting the left, front right, and right range parameters. And then soon enough, once it finds a direction to go ahead with, the robot will start moving.
Okay.
There you go. The robot is already moving. You can see it says moving forward. That's green. And this is supposed to be a naive one, so it's not the best, but then essentially it checks all its ranges around. And then it chooses which is the best direction to move forward with. And that was a naive optical avoider. We will let that run in the background. And so then I'll also put up the robot statistics one. So this one is essentially a running dashboard of various parameters and statistics you'll see. And there you go. As you can see, we can maybe enlarge some of this. But as you can see, it starts telling what's the distance covered, current direction, odometry position XYZ, and odometry position RQY, and lastly the IMU, or angular velocity, and the XYZ, and the acceleration in the XYZ directions. And this will keep on running in the background, especially it will keep on also changing as you can see the values, as the optical avoider autonomously moves the cursor robot around the course. And I think that was the two programs. That was on the real robot. So I'll try demonstrating this exact same thing in the gazebo simulation.
Sure.
For just 5 or 10 seconds, we can let this run. Let's see if it works.
Alright. It's doing well so far, so.
Yeah, it's not. I'll show you. Yeah, it just randomly chooses the direction based on the threshold values and what it thinks is the most distance.
Okay, so it prioritizes the furthest distance possible. That's the direction it will take. Alright.
And with this, we can also maybe open up the gazebo simulation.
I think you probably need to disconnect so that you can run your code in the simulation. Yeah.
Okay, I'll do that. I'll turn that off.
Okay.
restart everything. But this time, right from the zero simulation, I was put in some Linux commands that we were given. I'll just so except so for both the real and the simulation, it's essentially the same commands, except for one command because there's code that right. First you open the simulation, and then you open the tryoff that helps to move the robot in case something goes wrong.
Yes.
The robot interface. Fourth is the avoider, and then fifth is statistics. The only thing that you change between the real and the simulation is the first step, because in the first step it's either the simulation or the real robot. And so this time, instead of starting with the real robot and doing the program, we started with the zero simulation.
Right.
And then we run the next four same set of commands.
Okay. All right. There we go. We already have our first steps. Select the graphical tools. Yeah, I think slowly you see them both. It works also on the simulation. You can see already on the graphical tool that there's half the robot is falling, and then we use behind leg marks. Okay.
Yeah, and then we can also see the obstacle avoided program. It's being able to detect set the parameters successfully, and then time to move forward, moving forward correctly, checking all the different parameters, the left, right, etc. And then it draws a path on the screen.
It's still considering itself to be moving forward, not going.
Yeah, because it's being
Oh, okay. It realizes there's still some distance to cover before I crash, so to say, right?
Yeah, let's just go for it.
All right. Okay, let's wait for it to see.
Because the way the logic works for the program, right, is that it moves enough so that when it faces front, there's space to move.
Okay, so.
And then once it finds the direction, right now it's you can look at the direction, right? The robot statistics one. To note direction. Now, even though perhaps you can see the right direction has more distance, it keeps on moving until it maxes out the front direction.
Oh, right.
Out the front, and then it finds again the maximum. Is it the right? Is it left? What is the most distance?
Right.
It turns to that direction and then maxes that out.
And
then it keeps on running that.
Yeah. That makes sense. Makes real sense given what it was doing when it was facing the way it was trying to get to the minimum distance possible before making the turn. Okay.
Making the turn again.
Yeah.
Yeah. I think that was all.
Yeah. Okay. So.
Maybe,
yeah, let's get into the code now. I think we have seen that it works in simulation and the real robot, right? The real robot being most important. So let's see how you did this. So you can start with the naive obstacle avoider. script first.
Do you want me to show the actual code or just explain it?
No, the actual code, yes.
Okay, actual code. The IDE.
Did you have any slides that you wanted to use?
No, I have some notes. I think I'll just prefer talking over.
Right, it's all good. So let's get to the code, then you can be explaining as we go.
Start up with the that full screen.
Yeah, that's good.
So this is the bash script I created.
Mm-hmm.
And yeah, I mean, as you can see, I take essentially we were given what to do,
Mm-hmm.
what the functions were, what the variables were, what the parameters were not given.
Mm-hmm.
And so I took inspiration from the robot functions.bash script. I looked at what were the variables that we had in mind
Mm-hmm.
that could get the job done. The generation decided that I had initially created in part, I believe it was part 2.
Mm-hmm.
I did this in part 2, and then in part 3 we were supposed to create this obstacle avoider.
Mm-hmm.
And so, for example, if I didn't get the left scan, I looked at the robot functions dash script and then see which function is the most appropriate for that.
Mm-hmm.
I said, okay, it must be get scan left right, and I just use that.
Okay, can you tell me something about those functions, right? I want you to go back to that script, the one with your getter functions. Right, so if you use this function, these functions, right? But can you tell me what AWK then print $4 does? What do you understand what that does? Can you give me your perspective on the function?
So, to my understanding, I actually searched this up and I was kind of curious on what AWK does.
Mm-hmm.
And it's supposed to be, it's not exactly print, but it's one variation of print.
Mm-hmm.
The way I've used it, at least we were given to use it up here, right? They essentially just help print the variable, like onto the kind of like publishes it.
Yeah, but yeah, okay. I would say yes and no because I'm trying to probe you to explain to me why is it done that way, right? Or if we know we are getting some particular variable, right? But which one specifically? What is the significance of using the $4, for example, right? Why the function AWK? What are you trying to do when you use that function for selecting the variable you're going to print?
I mean, yeah, the dollar sign is just, that's the convention for all variables. So any variable, when you have to call upon the variable, you have to use the dollar sign.
Mm-hmm.
Yeah, as for the AWK, I'm afraid I don't know exactly like what the precise details are.
Mm-hmm. All right. So I will let you off the hook on this one. So what it does, it goes and selects the fourth argument, right? So it measures which variable based on the spaces or the white spaces if you are using any text editor, right? So based on that separation, it counts 1, 2, 3, 4 and picks the fourth one. So with these functions, we are having our variables being selected from the fourth argument after the third white space, something like that, right? So that's what is going on there. But yeah, okay, let's go to the next one. Can you explain to me, just pick one of your laser processing functions, right, in your knife obstacle avoider, and take me through that logic that you were saying. It has to pick the north direction and consider whether the right or the left are free, right? Can you take me through the logic of any one of those?
Sure. We can go to the first one anyway. The first one essentially, so first, before anything, right, it checks out what the left-right range is, the front left-right, etc.
Mm-hmm.
And it checks if it's free, and free meaning if it's underneath the threshold,
Mm-hmm.
threshold being 0.3 meters.
Mm-hmm.
Yeah, you can find it here. So it checks if the front range, for example, is less than the threshold, and if it is, then it would not be considered free.
Mm-hmm.
But if it is more than the threshold, then it will be considered free.
Mm-hmm. And in those
Based on
functions,
that,
okay, in those functions, I see you've got BC and then stroke L. Can you explain what is the relevance of that? Why do you need that in your functions?
sorry, are you talking about the echo or the BCL? I couldn't hear you.
The BC, then stroke L, right? What significance is that? Is it there for?
Okay. I think the BC one, that converts. It's like it's used for all, like true or false. Like I forgot how to say, but like comparisons. Whenever there's a comparison, right? The example it's appears less than or more than threshold. Once that happens, the BC minus all is used to convert that into a 0 or 1 value, a binary value, and then that assigns it to front free based on that assignment.
All right, let's go on. Can you continue explaining the logic that you were describing right now about the laser processing? Yes.
And then if it is free, then it will be if it's free, then obviously the front left free variable will equal to 1.
Mm-hmm.
If it's not free, then it will equal to 0.
Mm-hmm.
And then so based on that, so let's say example front left is not free, front free is not equal to 0, meaning it's not free either, and then front right is not free either.
Mm-hmm.
Then it checks, since everything is not free, it checks left or right, and then from the left or right it just checks which one is more.
Mm-hmm.
So which if the right scan range is more than the left scan range, then the what will come to the right. If the left scan range is more than the right, and vice versa.
Mm-hmm. All right. All right.
Yeah, and then I think one thing up here I did notice that it was not given to us is that once you turn it, so this was the way like we use this as the angular speed. Once we turned it, there was no sleep time, which I think I had to implement to make sure that there's a tune delay. Because I actually saw this in a simple control, right, where once this is all done, there's a sleep time, and we set it back to 0.
Mm.
This is not at least given to us in the optical avoider one. So I implemented a sleep time and then set it back to 0. So it turns, so it uses the angular speed for 1.5 seconds, and once it turns, it stops after 1.5 seconds.
Okay.
And
Okay.
it sets it to the angular speed to 0. Yeah.
Oh, okay. So you use the timer to determine for how long it is to turn, and then setting it back to 0 so that it stops the angular velocity. Okay. It zeroes it out. Okay. Okay. All right. Do you have any other bits that you want to show us? Any other sections of your code that you want to really get into details? The simple patrol script, I see you've got it there. Did you use it in any way? Does it work in conjunction with obstacle avoider?
Not really. I just use that as a reference.
Mm-hmm.
It was really underdeveloped, and I thought that I'll just leave it there in case I want to come back to the to just see how. Because it doesn't work perfectly, right? When I tried running, it always just worked.
Mm-hmm.
So when I was just testing out my code, I cross-reference, cross-examined, did the simple patrol bash script,
Mm.
and then just built my obstacle avoider bash script based on that.
Okay, so when did you run it separately? At some point when you were testing and figured out it works better? Like, yeah.
Because sometimes I used to get like these small errors, and I was like,
Mm-hmm.
And like when the program was not like, because without the timer, right, the thing was not working properly, and so I was like, something is wrong, and I was like, the simple patrol script works at least better than this one. So I just looked at it and found out, oh yeah, it has a sleep time, the timer, and it sets it back to 0. That's one of the biggest, I think, discoveries from there.
All right.
Everything else was, I just essentially not copy pasted, but just had to look at how it works out, like how the logic works out and what it does. And like, because the example up here, when it sets, it publishes to the CMD, that is 0.3146, that turns to left.
Mm-hmm.
And then when it's negative, that turns to right. Like those small kind of hints I got from simple control that script.
Okay, so if you were to list the improvements that you made from that script, right, what would they be?
Okay. First would obviously just be the syntax, because I was new to Linux, so I think the small like syntax things, like example the dollar sign, and then the BC minus L. I was not used to them. They're coming from a Python background, so that was one for sure. And then second, I would say um, was again the other hints I got, like mathematically speaking, about the 0.3146, negative 0.3146, and like how was the logic, and that turns left, the other one turns right, etc., etc. And then I think the third one would be the biggest one. Obviously, would be this one, where with the sleep timer and how that is required to make the robot turn.
So,
Stop.
okay, can you tell me what happened when you didn't have the sleep timer? At least give a gist of why it's so relevant to have that sleep time.
Yeah, because it didn't turn, like there was no sleep time, right? So there was no, like, for example, without a sleep timer, the robot would just keep on turning in the left or right direction,
Okay.
and then come back, and then it
So
would
it,
then evaluate, like once you do that, once the script runs, right,
yeah.
it's constantly movement, let's say the left direction, right, and then this and then it does this, it checks, it gets a scan range, but the scan range is more like instantaneous, right, because it's constantly moving. It gets some random range from some direction, direction,
Okay, what if
and then
the
uses that to evaluate.
okay,
Keeps on turning, like yeah.
so when you set angular velocity, do you zero out linear velocity as well, or before you had implemented the sleep time for the angular velocity, did you make it stop first and set angular velocity separately?
Yeah, for the angular linear velocity, that was initially already set to 0, right? And so when you have one of these if conditions come out to be true, only the angular velocity is changed, and then let's say after 1.5 seconds, it's already set back to 0. It's still both of them are 0, and then we only really change either angular velocity or either linear velocity in the case that the front direction was open. For example, up here, the front velocity, the linear velocity was set to 0.1, but as you can see, angular velocity must have been 0 before this. So once it's set to 0.1, again to sleep, and then back to 0. So either you're moving angular, you're turning, and then once you stop there, you move ahead.
Okay, so you had to separate them so that you don't have concurrent setting of angular and linear velocity. All right. Thank you very much. Jamin, is that right? Yes, Jainam, right. Okay.
Yes, that's right. Yeah.
So, all right. Thank you so much for a wonderful presentation. So, what we'll do is we'll wrap it up here and we'll just sign out. All right, everyone. This was Jainam's presentation, and congratulations to him. Would like to encourage all those of you who would like to come and showcase their work to also do the same. And